Hello and welcome to your Algebra 2 lesson 5.7. Today we're going to apply the fundamental theorem of algebra, and so we're going to classify the zeros of polynomial functions. So a little background. The equation x cubed minus 5x squared minus 8x plus 48 equals 0 becomes x plus 3 times x minus 4 squared equals 0 when factored. It has two distinct solutions, negative 3 and 4. Because x minus 4 occurs twice, you can see it's squared right there. 4 is considered a repeated solution. Specifically, it's called a double solution or double zero or double root. So, with 4 counted twice, this third degree equation has 3 solutions. This can be generalized into the fundamental theorem of algebra. Thank you, Carl Gauss. The fundamental theorem of algebra states if f of x is a polynomial of degree n, where n is greater than 0, then the equation f of x equals 0 has at least one solution in the set of complex numbers. And a corollary of this is if f of x is a polynomial of degree n, then the equation f of x equals 0 has exactly n solutions, provided each solution repeated twice is counted as 2 solutions, each solution repeated 3 times is counted as 3 solutions, and so on. So how many solutions does the equation x cubed plus 5x squared plus 4x plus 20 equals 0 have? That's right, it has 3. In fact, they are negative 5, negative 2i, and 2i. How many zeros does the function f of x equals x to the fourth minus 8x cubed plus 18x squared minus 27 have? That's right, it has 4. And they happen to be negative 1, 3, 3, and 3. So it has negative 1 as a unique solution and 3 is a triple zero. All right, we're going to find all the zeros of f of x equals x to the fifth minus 4x to the fourth plus 4x cubed plus 10x squared minus 13x minus 14. Okay. Find the rational zeros of f like we talked about in 5.6. Because f is a polynomial function of degree 5, it has 5 zeros. The possible rational zeros are plus or minus 1, plus or minus 2, plus or minus 7, plus or minus 14. Let's look at the graphing calculator to see which values might work. So looking here, look how it comes up and barely touches the x-axis. It's tangent to the x-axis right there. That means we probably have a double zero right here at negative 1. Okay, that's what a double zero looks like. If you get really close to it, it looks like a little quadratic because there's 2 factors that give it to you. So I'm betting we have a double zero at negative 1, and then it just crosses the axis linearly here at x equals 2. So I bet we have a double zero at negative 1, so that counts for 2 zeros. And then we have 1 here at positive 2. We should have 5. We've got 3. That must mean the last 2 are imaginary. Okay. All right. So like I said, negative 1 appears to be a double zero and 2 appears to be a 0. Let's check with synthetic division. That will also help us get our function where we can get it down to a quadratic. All right, so first thing we're going to do is we're going to test negative 1. So we've got negative 1, and we do the synthetic division with it, and we end up with a remainder of 0. So now we know that f of x equals x minus negative 1, so x plus 1, times x to the fourth minus 5x cubed plus 9x squared plus 1x minus 14. So since we think negative 1 is a double zero, we want to try it again with the quotient polynomial. So if you'll notice, we take these values here, and we're using them as our top row now, and we're doing negative 1 again. So we bring down the 1, 1 times negative 1 is negative 1, and so on, and we end up with a 0. So we've just shown that negative 1 is a double zero, and that f of x equals x minus negative 1 times x minus negative 1 times x cubed minus 6x squared plus 15x minus 14. So we want to take these coefficients from this quotient, and we want to try the 2 and see if that works. Okay, so here we have 2, and we brought down the 1, and 1 times 2 is 2, and so on, and yay, it works. So now we know that we have negative 1, and 2 as zeros, and f of x equals x minus negative 1 times x minus negative 1 times x minus 2 times x squared minus 4x plus 7. So finally, we're down to a quadratic factor, a quadratic quotient. So we can, here we have that f of x equals x plus 1, which is x minus negative 1 squared, times x minus 2 times x squared minus 4x plus 7. So now we could try to factor, but it's not going to work. So anytime you suspect that you're going to have imaginary zeros, you're going to have to use quadratic formula. So on this one, you might as well just go straight to it. So x equals 4 plus or minus square root of negative 12, once you've simplified a little. Well, we can put our I out and then break 12 into 4 times 3. Square root of 4 is 2, so we end up with 4 plus or minus 2i square root of 3 over 2. We want to try to reduce this, and it probably is easiest is if you reduce it by splitting it up at the plus or minus. So do 4 over 2 plus or minus 2i square root of 3 over 2. 4 over 2 reduces to 2 plus or minus I square root of 3 because your 2's cancel. So the zeros of f are negative 1, 2, 2 plus I square root of 3, and 2 minus I square root of 3. And just like the fundamental theorem of algebra tells us, there's 1, 2, 3, 4, 5 zeros. Okay, complex conjugate theorem. If f is a polynomial function with real coefficients, a plus bi is an imaginary zero of f, then a minus bi is also a zero of f because they're generated by the quadratic formula, the whole a plus or minus square root, the whole, and so you're going to end up with a plus bi and a minus bi. It gets a little confusing because we've got a and b here, and the quadratic formula is negative b plus or minus, all that stuff. The whole thing is because it comes from the plus or minus, you're going to have the conjugate. Same thing with irrational zeros. They're going to come in conjugate pairs too. All right, so we want to write a polynomial function f of least degree that has rational coefficients, a leading coefficient of 1, and 3 and 2 plus square root of 5 as zeros. Well, because the coefficients are rational and 2 plus square root of 5 is a 0, 2 minus square root of 5 must also be a 0 by the irrational conjugates theorem. We're going to use the 3 zeros in the factor theorem to write f of x as a product of the factors. So we're going to have x minus 3. Actually, I think there might be a little typo here. A leading coefficient of 1, right? Okay, so there are 3 factors, 3, 2 plus square root of 5, and 2 minus square root of 5. All right, so we're going to multiply x minus 3 times x minus 2 plus square root of 5 times x minus 2 minus square root of 5. So we're going to regroup the terms if you want. If not, you can just simply distribute the negatives there. But this is one way to do it that might make your life a little easier. If you go, oh, okay, this is x minus 2 minus square root of 5. I can do x minus 2 minus square root of 5. This is going to be x minus 2 plus square root of 5, so I can consider the x minus 2 together and then plus square root of 5. If not, just factor it normally. But if you do regroup this way, you can use the difference of 2 squares that the middle terms would cancel out. And so you're going to get x minus 2 quantity squared minus 5. So you've got to expand the binomial on the inside. So we're going to have to FOIL this anyway. So you're going to have x squared minus 4x plus 4. And then we're going to subtract 5 from that. So that'll be x squared minus 4x minus 1. And like I said, if that gets too confusing, just distribute the minus, and just keep doing repeated distributive property. Okay? And you should still end up with x squared minus 4x minus 1. Now we're going to do repeated distributive property using the x minus 3. So let's see, that's going to give me x cubed minus 4x squared minus x. Then come back with the minus 3, so negative 3x squared plus 12x plus 3. And we're going to combine terms, and we're going to get x cubed minus 7x squared, negative x plus 12x is 11x, and then plus 3. Okay, Descartes' rule of signs is another way that, especially if you don't have your graphing calculator with you, once you've got your rational zeros, you might want to be able to limit which ones you plug in, and sometimes knowing how many positive zeros that you're going to have or negative zeros you're going to have can be helpful, and also knowing kind of how many imaginary zeros you might have, that would be helpful too. So it's just another way of helping us have a clue what values to try, especially if you don't have a graphing calculator. So we've got our polynomial function in standard form. The number of positive real zeros of f is equal to the number of changes in the sign of the coefficients of f of x, or is less than this by an even number. Okay, so you count the sign changes and you start subtracting 2 until you get to 0 or a negative value, and then you stop. The number of negative real zeros of f is equal to the number of sign changes in the a number of changes in sign of the coefficients of f of negative x, or is less than this by an even number. Again, you just keep subtracting 2 until you get to 0 or a negative number. Alright, so let's look. We're going to determine the possible number of positive real zeros, negative real zeros, and imaginary zeros for f of x equals x to the 6th minus 2x to the 5th plus 3x to the 4th minus 10x cubed minus 6x squared minus 8x minus 8. Okay, so we start counting sign changes. So for f of x, positive to negative, that's 1. Negative to positive is 2. Positive to negative is 3. So there's 3 sign changes. So f of x either has 3 positive real numbers. Okay, so that's one possibility. Subtract 2, you get to 1 positive real number. Subtract 2 again, that'd be negative 1. You can't have negative 1 of something. So f either has 3 positive real zeros or 1 positive real zero. So we make note of that. Now we look at f of negative x. So we have negative x to the 6th power minus 2 times negative x to the 5th power plus 3 times negative x to the 4th power minus 10 times negative x to the 3rd power minus 6 times negative x squared minus 8 times negative x minus 8. All right. Negative x to the 6th power, you're going to be multiplying a negative x times negative x times negative x 6 times. An even number of negatives being multiplied together is going to be positive. So there's no sign change there. It's just x to the 6th. Now, negative x to the 5th is going to simplify to be negative x to the 5th. You're going to have a sign change because you're multiplying a negative times itself an odd number of times. So you're going to have negative 2 times negative x to the 5th, so you're going to get a plus. Negative x to the 4th is negative x times negative x times negative x times negative x, so it's just going to be x to the 4th. All the negatives multiply away, so you're going to have plus 3x to the 4th. Negative x cubed, that's negative x times negative x times negative x, which is going to be negative x cubed times negative 10 gives you a plus. Negative x squared is negative x times negative x, so just x squared, so you're going to have minus 6x squared. And then negative 8 times negative x gives you plus 8x, and then you're minus 8. Okay, guys, when you compare f of negative x to f of x, any term that has an even power of x, the signs are going to be the same. Any term that has a negative, an odd power of x, the signs are going to be opposite. So a really quick way to do this is just to go through and go, okay, x to the 6th, got to change this, plus 2x to the 5th, plus 3x to the 4th, got to change this one, plus 10x cubed. This one's x squared, so no sign change, so minus 6x squared. 8x, that's x to the 1st, so minus 8x is going to be plus 8x, and then just minus 8, the constant never changes. So that's a quick way to do f of negative x. All right, now we want to count sign changes. So let's see, it's positive, 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 positive to negative, that's one sign change. Negative to positive, that's a second sign change. And then positive to negative, that's a third sign change. So again, there's going to be, since there's 3 sign changes, f either has 3 negative real zeros or 1 negative real zero. All right, so here's what you need to do. You need to make a little table, okay? And you need to come up with You need to have one column for positive real zeros, one for negative real zeros, one for imaginary zeros, and one for the total number of zeros. You look at the degree of the polynomial to get the total number of zeros. So since it's 6, this column is always going to have 6's in it. Okay. Now, what you do is you take your first possible number of real zeros. There were 3 was our biggest number, and you match it with the biggest number for negative reals. So if there's 3 positive reals and 3 negative reals, that's 6 real zeros out of a total of 6 zeros. So that means we have 0 imaginary zeros. Okay. Now you match up the biggest possibility for positives, so 3, with the next possibility for negatives, so 1. 3 plus 1 is 4. Well, we need to get up to 6, so that means we must have 2 imaginaries, if this is the case. Okay, we've matched up each possibility for negative real zeros with the largest for positive. We've matched 3 with 3 and 3 with 1. So now we're going to go to the smaller possibility for positives. So we've got 1, and that could be matched with 3 negative zeros, real zeros. So that's 1 plus 3, which is 4. We need to get up to a total of 6 zeros. So 6 minus 4 is 2. That means we would have 2 imaginary zeros. It could possibly be that there's 1 positive real zero and 1 negative real zero. That's only 2 zeros out of 6, which would mean we have 4 imaginary zeros. So one thing students sometimes wonder is, well, why do you subtract 2's? Why don't we go 3, 2, or 1, or 0 negative real zeros? That's because imaginary zeros always occur in pairs. So what this is saying is you either have 3 positive real zeros, or you have 1 positive real zero and 2 imaginary zeros that are faking out as a positive 0. Okay, you either have 3 negative real zeros, or you might have 2 imaginary zeros that are faking out as a negative real zero. So these are all the possibilities. Trust me, as you practice this, you'll get the hang of it. Okay, guys, that's it for today. So go ahead and do the problems to try on your own, and come to class ready to go over them and to do the classwork. I will see you in class next time. Have a good day. Bye-bye.